All right, welcome to episode 2 of Information Theory, hosted by myself, a mad coder at What Codes at Midnight, and you might find that a very fanciful name. We are all about interactivity, and so I'm going to take some time to already answer some questions of somebody who's working along InventiveHarvest with the notebooks and has some great videos, which I'll also link. I'll be putting this notebook up at the notebook link, and I'll put that down below too. It might take me a while after it first publishes to follow up and do all that. All right, so a couple things that InventiveHarvest asked and that we'll go over, and little related things. So one thing is that one way to get everything clean, and look at these numbers here, is you can sell all output clear, right? So that kind of starts over. Something else that doesn't clear the cells but does reset the Python interpreter is to restart the kernel. You could do that in the you could do that with this button, or let's see. Oh, kernel, of course. Interrupt and restart. Right, but you can also do that by hitting escape to make sure you're not in the cell and then going 0, 0. As a matter of fact, there are a lot of keys that are useful. I can create the cell below by hitting B, or above by hitting A. I can delete the cell with X. All right, and you could see all those just by pressing H. Okay, or if you don't even remember H, you can go up to keyboard shortcuts. And there's a lot of shortcuts. Now, one I use a lot is I don't run all the cells at once. I usually start at the top and then hold Shift-Enter. That runs the cell and goes to the next cell. Okay, and so what I did here is I also use this init printing function that comes from Sympy that'll print the formula quite nicely. Here's the symbols. Here's me making f a formula f and taking the differential of it. Now, don't ask me to explain derivative versus differential, but I won't get out ahead of you. We'll see what you're trying to do, and I'll help understand the Python to help you do it. I've used Sympy in the past, but it's been a long time. An example of where you would use Sympy in numerical processing is to keep track of variance or error data. If you have an image, a two-dimensional image, you might also keep that two-dimensional variance data. And when you combine images, say you multiply one image by another and divide it by another, to combine the variance of all those images, you don't do the same mathematical operation. You have to do it using a derivative. And don't ask me to tell you right now the difference between a derivative and a differential. Differential is a little part, and the derivative is like two of them with respect to each other or something. Anyway, you can get derivatives in Sympy too, but with the diff you get an actual function that you can evaluate. So here's me taking those two things, and you see the result of the init printing use Unicode equals true is that it prints much nicer versions. Without that, actually, we can look real quick. I'll reset the kernel, and we see that it draws it like this in sort of a more regular computer text, Python looking, right? So looks much better with this, and we see that it took did the differential right of f with respect to y. And then what you can do is here I'm setting x0 and y0 to this, and I'm using a little trick, right? I could have written just x0 equals 2 point and y0 equals 3, and that would have been the same, right? But I'm using this little tuple trick. So in Python, the parentheses is a kind of data structure, and you can set two individual variables to it, and this just means that x0 is going to be 2 and y0 is going to be 3. All right, so this cell sets these values, and then what it does is it takes it's going to print into a formatted string. So I'll break this apart real quick. The x and y and the evaluation, right? So f dot eval f And this is the substitution. So I'm saying for x, substitute x0, and for y, use y0. Okay. Okay, and then I'm doing a similar thing for the differential. And so instead of f dot eval, it's f underscore diff dot eval, eval f. All right, and if we run that, you see, I think you'll see those are calculated correctly. If we set this to be 1, let's see, we get an easy ones to check, because 1 plus y, or 1 cubed is 2, and 1 cubed times log of 1, which is 0, is 0. Right? Okay, so now I will show a little bit, because I want to do both, just show the big picture, whole notebooks, how we play with it, and things like this. And I just remembered something else I wanted to do in this video. We can do that later. But you know, I also want you, the Python, to be able to soak in if you might be a Python novice. So I'm going to show you what I've done up here. So here I have this tuple that I'm passing, percenting into this string, and what's going to happen is the first element of the tuple, and there's other more modern, better ways to do this actually. X0 is going to go in the first spot. %f is a format that says it's going to be a floating point. Y0 is going to go in the second one, and whatever this returns is going to go in the third one, all expected to be floats, right? So if I just do, you know, value equals f, eval f, subs equals x, and we'll see what value is, 2.0, right? So that was the number that got inserted into here, right? That's this 2.0. But when I format it this way, it printed it out with a different way, because this is just letting ipython show it. If I go, so you get that, and if I go, see. All right, what I forgot to do is I was going to use matplotlib to plot this thing. Don't think that'd be hard, but I don't think I want you to watch me figure out how to feed one of these functions into matplotlib live. So I guess that'll be something we can do next in this notebook. So I'll publish this notebook. My next planned episode is to go over the data notebook, the random data notebook again, with an eye towards how we can be a little bit apathetic and see patterns where there aren't any. The mathematics can extract a pattern that might just really be noise, and so this is part of the art that we'll be trying to master as programmers, not as the data scientists, or not as scientists and data analysts directly necessarily, though we'll do a lot of that. It's fun, and if that's your purpose, this would be a good way to go. But we're going to look at it from a programmer's point of view in a lot of practical ways, and we're going to try to keep it fun by using a lot of visualization. All right, so one thing also I wanted to mention in answer to a question is these numbers over here. This is just what's last ran. You can see here currently the biggest one is 12, so the next one I run will be 13. If I rerun this cell, it's going to become 13. If I go down, they'll get an order again, because it's the last one that ran, and this is because we don't necessarily run all the cells at once, because usually this is the point of the notebook, is for it to be interactive. Now let's say you had a notebook doing a lot of good work and you really just wanted to run it as a script. Yeah, then you could run all of them and it'll run from top to bottom. But as I say, what I normally do is start at the top and everything will have been reset. You know, it starts off reset. Well, not necessarily, but no more on that later. And I can run through one at a time until I get to the point where I want to play around and do something. Okay, so yeah, and a little bit more about some of these packages you mentioned. So Sympy, and I'll just mention this over and over actually, but so Sympy is for dealing with symbolic math when you want to deal with the formula as the formula. If you need to play with formula, you want to do that as symbolic expressions before you go evaluate them. And you'll find in computer science, of course, this is a fundamentally different thing. Computers do not do math that way. When we think of computers as these mathematical computing machines, they are in fact not very mathematical, but very procedural and just step-oriented. And they happen to know how to multiply and things like that through various algorithms. And often they're approximations available to discrete mathematics. You know, when a computer calculates a sine, you know, it doesn't do any mathematics. It could even have a table and interpolate, or it can try to zero in. There's methods to zero in on a value. When it takes a square root, it's not the same thing as when you take a square root in the mathematics. You actually have to perform this operation in the computer that introduces noise, because you don't have a continuous number line in the computer. You essentially have a discrete number line, 1, 2, 3, 4, 5, and you can pretend it's 0.1, 0.2, 0.3, and so on, but there are mathematical limits to that. Sympy is a way to deal with the expressions. And NumPy, on the other hand, is for doing big number crunching. There's a lot of useful scientific functions in there because of this central role, but the central role basically is to be able to handle large amounts of data that'd be too big for a scripting language like Python in an efficient way. Right, there's also another great library called Pandas, which is more useful in business analysis, though it comes up in everything, and it is for table-oriented data. And you can load Excel sheets, do SQL queries, and then have huge tables in memory and do number crunching on them. And that uses Pandas, as do a lot of systems for particular scientific disciplines. You got your own OSGeo in georeferencing, open source georeferencing software, and it also uses NumPy. Matplotlib will come up a lot. That's what we're going to use to plot things. But we'll also look at some JavaScript plotting tools coming up soon. The kwargs thing, I don't think. Well, let me just tell you, that's the keyword arguments. So there was some sort of a problem, like you gave it a keyword argument it didn't like, and so it just happened to come up in that complaint of that. What you're looking at is an exception, a call stack generated by an exception being thrown. Now, another thing is that with getting help, some things that seem built in, I can get this help on. Now, this question mark, of course, is an ipython thing, not a Python thing. So, okay, that's because int is an object, even though it's built in. But for some things like the if, you know, I can't get help on the if that way, because it's not an object. It's a keyword, and so def is also like that. So let me show you how def works really easy. Basically, it's just the way you define a function in this particular language, and Python works like this. You say def, and then function name, and then the parentheses for the arguments. So let's say the arguments are a and b. And then we're going to print A and B. And I'm going to use that formatting thing again, like that. So A will go in the first place, right? And I can also return a value. So we'll just return 5 from this. Okay. Now the features of this is that you have to have a colon here, and then Python cares about this white space, so each line has to be indented. Usually it's 4. You can see it's doing that for you, but as long as they're the same, it could be like that. Okay, now I can call that. So let's say A equals function name, and then parentheses, but we're going to put the values we want in here. So we'll make them strings. And it prints Python and NumPy just as the function was told. And you could put dirty words in there if you like. And then what's A as a result? Well, it's supposed to be 5, right? So it's 5. All right. All right, I hope that that was useful. And next we'll look a little bit more at the fitting. I enhanced a little bit the way I'm generating the so-called random data, the simulated data. And we'll get back to that. I mean, I might do something in the meanwhile, but that's the next planned one. All right, thanks.